Here we are at part 2 of our proof that the sum of a rational number and an irrational number is always irrational. So we've written the statement in P implies Q form. Our hypothesis is P. Our desired conclusion is Q. And in a proof by contradiction, we assume that P implies Q is false, and that is logically equivalent to assuming that P and not Q. In other words, P is true and Q is not true. So we assume P, which is assume N is rational and S is irrational, and we also assume not Q. So we also assume N plus S is rational, and we wish to arrive at a contradiction. The only part of our hypothesis that is not going to yield an equation is this part, that S is irrational. So what in the world do we do with that? Well, this is exactly what we are going to contradict. How do we contradict this? We contradict it by proving that S is rational under these conditions. A number cannot be both rational and irrational, hence we will arrive at the desired contradiction. So here goes. We've assumed that N is rational, and we've also assumed N plus S is rational, and we like this because we get our equations. So by the definition of rational, we may write, I'm going to do them both in one fell swoop here. N is equal to, let's say, A over B, where A and B are integers, and B is not equal to 0. And N plus S is also rational, so let's write an equation for that. N plus S is equal to, let's say, P over Q, where P and Q are integers, and Q is not equal to 0. Perhaps a better choice for variable here would be C over D for variables, but we're just going to use P over Q. Does it matter? Not really. Okay. We're going to use the fact that N plus S is always equal to N plus S. So observe, N plus S is equal to N plus S. Now, how are we going to use that? Well, we have an expression for N, namely that N is equal to A over B, where A and B are integers, and we also know that B is not equal to 0. This is all hypothesis, proof money. We also have the equation that N plus S is equal to P over Q, and we know P and Q are integers, and Q is not equal to 0. Three-part definition of rational applied to both N and N plus S. So to emphasize what we're going to do, I'm going to put a parenthesis around N on the left-hand side of our tautology, N plus S equals N plus S, and a parenthesis on the right-hand side encompassing all of N plus S to indicate the substitutions that we're going to make now. So observe, N plus S equals N plus S. It asks, to continue my sentence, A over B plus S is equal to P over Q, where we know A, B, P, Q are integers, and both B and Q are not equal to 0. But let's solve for S. What is it? It's P over Q minus A over B, which of course, getting a common denominator of QB is PB minus QA over QB. And let's take a breath there. Our plan is to show that S is rational, to contradict our assumption that S is irrational. We're at part 1 of the definition of rational. We have written S as a quotient. Now we have to verify part 2 of the definition of rational, namely that the numerator and denominator in this quotient are both integers. To do that, we use the closure properties of this set of integers. Since Z is closed under, well, what are the operations we're using here? To build PB, we use multiplication. Same with QA and QB. So we're using multiplication. But we're also using subtraction, which is actually addition. We're adding the additive inverse of QA, but we can say subtraction. That's fine. Since Z is closed under multiplication and subtraction, we can say, now we have to speak to the entire numerator. PB minus QA is an element of Z, and we have to speak to the entire numerator. QB is an element of Z. All right, we have part 2 of the definition of rational satisfied for the number S. We have the equation, part 1. We have that these pieces, the numerator and denominator, are integers. The last thing we need to do is verify that QB is not 0. The denominator can't be 0. And so we are going to invoke the zero product property. By the zero product property, we'll just say ZPP, since B is not equal to 0 and Q is not equal to 0, we can say QB is not equal to 0. So we have now satisfied all 3 requirements in order to say that S is rational. This means S is rational, which contradicts our hypothesis that S is irrational. And I'll sum it up with a shorty because I only have a little bit of room here and I really don't want to use another page. So if N is an element of the rationals and S is an element of the irrationals, which is the reals minus Q, then N plus S is an element of R minus Q. It just fits, just barely. And that ends our proof that the sum of a rational number and an irrational number is always irrational.